In the last video, we covered switches, a type of sensor that can only be either on or off. In this video, we're going to cover digital sensors. These are types of sensors that use multiple switches together in order to be able to have more than just two values. We'll start our study of digital sensors with the Hall Quadrature encoder. A Hall Quadrature encoder is one type of sensor used to measure rotational position. It is a digital sensor, which means that it can measure only certain large enough increments of the physical quantity. This is as opposed to an analog sensor, which can theoretically, although not actually, measure an arbitrarily small change in the physical property. Let me show you what this means. First, find the DC motor included in your kit. It looks like this. On the back of this DC motor, there is a Hall Quadrature encoder attached to it. Your Hall Quadrature encoder has two Hall switches on the back. They are switches, so they can only be on or off. First, plug in the cable to the encoder like this. Now, solder leads onto the wires. Start by stripping the ends of the wires. If you have a wire stripper, you can use that. If not, you could use a wire clipper like I'm using here, or even a scissors. Simply gently clip the end of the wire so that you cut through the insulation but not cut through the wire. And then pull on the insulation with your wire clipper or scissors or wire stripper to pull the insulation off and reveal the wire inside. After you've finished stripping all of the wires, take a jumper wire and wrap the encoder wire around the end of the jumper wire. We're doing this to try and get a good mechanical and electrical connection between the wires. Once the wire is wrapped around the jumper wire, we're going to solder these two wires together. Use your soldering iron to touch the joint, the place where these two wires are wrapped together, and get it hot. Then touch the joint with the solder to melt the solder onto the joint. You don't need a lot of solder, and if you have the soldering iron at a good temperature, the solder should easily flow into the point where the two wires are touching each other. This will give you a much better electrical connection than if you just wrapped the wires and didn't solder them together. So solder a jumper wire onto each of these encoder cable wires. Be careful that these wires don't touch each other while we're using it. It's a good idea to wrap a little electrical tape around each of these exposed wires if you have it. Let's set up the circuit like this. Connect the voltage of the Hall encoder to VDD on the PSoC. Connect the ground wire to ground of the PSoC. And connect C1 and C2 to the two LEDs in your kit like this. First, connect the C1 and C2 lines each to their own row of the solderless breadboard. Pick a row that's unused so far. We'll set up this LED circuit the same way we did back in the introduction. Remember that the LEDs have one end that's long and another end that's short. Connect the long end to the wire from the encoder and connect the short end to the row of the solderless breadboard that is on the other side of the center of the breadboard. So the LED bridges the center of the breadboard. Now use a jumper wire to connect the two rows that the short end of the LEDs are plugged into. Finally, take your 100 ohm resistor and connect one of the two LED rows to the ground rail of the solderless breadboard. Plug in the PSoC to the USB port of your computer. Now, rotate the magnetic disc slowly. The magnetic disc has several north and south magnetic poles. A Hall switch turns on when one pole is near it, and it turns off when the other pole approaches. As the magnetic disc rotates slowly, the switches go on and off in order, cycling through 4 states. White on alone, blue on alone, white and blue both on together, and white and blue both off. These 4 states are why this encoder is called a quadrature encoder. The prefix quad refers to the number 4. If we could use our microcontroller to count every time the state of the switches changes, and we know how many times the state changes in one rotation of the disk, we could back calculate the angle of the motor that is attached to this sensor. Try this. In your top design, find a quadrature decoder and drag it onto the screen. Also, connect 2 digital input pins to the A and B inputs. Double-click on the pins and rename them C1 and C2. Also, connect a clock to the clock input. Double-click on the quadrature decoder block to set its settings. First, uncheck glitch filtering like this. Now look at the Counter Size tab. Here you set the biggest number you will allow for the counter. If you make this number bigger, it will consume more of your chip's memory space. But if you make it smaller, the biggest angle of the motor you can keep track of will be smaller. Right now, we aren't in danger of running out of memory space, so let's select 32-bit. Now, look at the Counter Resolution tab. If you set 1x, you will get 1 count every time a change of all 4 states completes. If you select 4x, you will get 1 count every time one state changes to the next. In sensors, the term resolution refers to the smallest change in the physical property that the sensor can detect. 1x will give you a lower resolution, but you'll be able to measure faster speeds of the motor. 4x will give you a higher resolution, but it's more likely that if the motor moves fast, the counts could go by so fast that you could miss them, and that would throw off your sensor read. For now, we're not going to be moving super fast, so select 4x. Lastly, click on the Index Input. Some encoders have a third switch that triggers only once every time the encoder completes a whole revolution. That switch is called the index. Our encoders don't have an index line, so turn this off. Set C1 as pin 16 and set C2 as pin 15. Now in the C code, we'll add a start quad decoder line to the beginning inside the main function. Next, we'll create a variable to hold the count. Let's make it an int. Since we are just counting a number of pulses, this variable can't have a decimal point. Now, inside the for loop, let's add a line to read the quadrature decoder count and store it in this variable. Then show the count on the LCD screen. Okay, now program the PSoC. Let's go back to our robot. Right now, the C1 and C2 lines are connected to our LEDs. Unplug them and instead plug in C1 to pin 16 and plug in C2 to pin 15. Now slowly rotate the disc back and forth and watch the count on the LCD screen. Notice how the count number goes up when the disc rotates in the positive direction, which is determined by the right-hand rule, and goes down when rotated in the opposite direction. Now, carefully turn the disc one complete revolution. How many counts are there in one revolution? When you look at specifications of encoders posted by manufacturers or retailers, you will find a value listed as either counts per revolution, which is abbreviated CPR, or pulses per revolution, which is abbreviated PPR. This is what this number means. Now, let's do one more thing. Find the DC motor horn in your kit. It looks like this. Carefully press the horn onto the DC motor shaft. You will notice that both the shaft and the horn have a flat. Line up the flats and then carefully press the horn on. Now, zero the encoder count by pressing the reset button on the PSoC. Now slowly rotate the horn one complete revolution. How many counts are there? Why is this number different than it was when you turned the disc one complete revolution? It is because of the gearbox on the motor. The encoder is attached to the motor shaft before it goes through the gearbox, and you are turning the motor shaft after it goes through the gearbox when you turn the motor horn. From this, we can deduce the gear ratio of this motor. Also, we can find the actual counts per revolution of this motor encoder gearbox combination, and thereby find the actual resolution. For example, we've just seen here that we have approximately 800 counts per revolution. Also, we know that one revolution corresponds to 360 degrees. If I now invert this calculation to do 360 degrees divided by 800 counts, we get 0.45 degrees per count. This is why this sensor is a digital rather than analog sensor. Any rotation of the disc, or in this case the motor shaft, that is less than 0.45 degrees, we cannot measure it with this sensor. Also, 0.45 degrees per count is the resolution of our sensor. 0.45 degrees is the smallest change in the physical property that we can measure with this sensor. We'll be doing this with a bit more accuracy when we get to the motion control section of class. Now, the encoder that we just hooked up and learned how to use is a Hall encoder. There is another common type of encoder called an optical encoder, which works a little bit differently. It is also a digital sensor, but instead of using Hall switches and a magnetic disc, it uses a photodiode, an LED, and a disc with slits in it. A photodiode is a switch that goes on and off in response to light intensity. The LED and the photodiode are positioned across from each other. Then the disc is placed between them and is attached to the motor shaft. As the motor rotates, the slits pass between the LED and the photodiode. We can figure out the angle of the motor by counting the number of on-off pulses from the photodiode. Besides photo versus Hall, there is another difference between different kinds of encoders: absolute versus incremental. An incremental encoder can only tell us how many counts have elapsed since the encoder was powered up. An absolute encoder can tell us the actual rotational position at any point in time, even if the encoder is powered down, rotated, then powered up again. It does this by using a disk with a bunch of concentric rings and a bunch of photodiodes like this. The transparent opaque pattern on the rings follows a specific pattern. The innermost ring has half the ring transparent and half the ring opaque. Then the next ring has 1/4 transparent, 1/4 opaque, then the next quarter transparent, and the last quarter opaque. The next ring alternates in eighths, then the next ring in sixteenths, and so on. Because of this pattern, every rotational angle produces a unique on-off pattern of the photodiodes. In fact, that on-off pattern corresponds to a number of bits. Each concentric ring is either transparent, giving a 1, or opaque, giving a 0. By reading the value of the bits from the absolute encoder, we can determine the rotational angle. The encoders that we learned about in this video are digital sensors. In the next unit of class, we'll start looking at analog sensors.